Okay, we're going to go back to this circuit again, and this is in fact my second attempt at doing this, so now I kind of regret not editing these videos because now I'm going to have to restart. But anyway, we're back to the 74HC595 fun. So this is it working here. So originally the whole point of the series was actually to talk about using this chip to add more outputs to your Arduino projects, but it's sort of turned into another little side project, and in this case here we're making a sort of little game thing where you can you can make a different pattern. So it's basically a pattern making toy, which is kind of working. I don't know if it's actually working the way it's supposed to today. I hope everything's wired up the same as it was before. Sorry, there's lots of flashy lights still everywhere. Why does this one not do anything? There's a little LED here that does nothing. But anyway, so we went through this whole, I went through all this stuff about, now where did I put the piece of paper that I just had? The fact that there are two clocks for this chip. So one of them shifts an internal register. So there's eight bits in the internal register, or eight registers that make up one big register. I don't know the exact correct term. But there are 8 internal bits of data that you can store, and they can be shifted along one when you send a clock pulse. So the rising edge of a clock pulse into the shift thing will shift the internal register, but it won't change what's being outputted until you do a rising edge clock into the latch clock pin. And the thing is, I want this to be automatic and kind of working like this. So I have to clock both of them at the same time, but that causes problems because it makes them out of sync. Because when you do the latch clock, it tends to latch what was in the register before you're doing the shift. If you clock them both at the same time, it does the latch first and then the shift second, and that creates synchronization problems, which doesn't matter when it's going really fast, but it does matter when it's going really slow. And so I went through this big series. If you go back and look over the previous videos, it was just a series of videos of possible ways of fixing this, and the way that I finished up with was with using a capacitor and sort of creating this smoothed out curve, which is going to trigger the latch clock a little bit later than the shift clock. So the black line there is the shift clock, and then the red line is the smoothed out and delayed latch clock. And so there's a bit of a delay between the two clocks. And I went through an elaborate way of showing that this actually is, well, I was telling you that I think it works because of the way that the way it feels when I press the buttons. And it feels like it works today, so that's a good thing. But of course, if you're watching this, you have no idea that I'm telling the truth. And it's probably very hard to tell that I'm telling the truth because you can't really see me pushing the buttons. So you have to take my word for it. And if I was doing this and I had a really cool equipment, then I'd use a dual trace scope, and then I could compare them on an oscilloscope, and I could see whether or not there is in fact a delay, and everything would be happy. And so we would be able to do that. But I've only got this little scope today, and it's only got one little input. So the question is, what way could I use to test this with only one trace? And so that's what today is going to be all about. I'm going to turn this off for a second, and we're almost up to the part where I stopped the video last time. So here are the two pulses. So this is my ideal, this is what I'm hoping is actually happening. I'm going to move that there. Oh, there's not enough room on the table. So that this is what I hope is coming through. I hope you're going to get this green shift pulse coming in, and then I'm going to get a delayed red latch pulse coming through. So all that matters is the rising edge on the clock. So when this one has a rising edge here, then you get a clock, you're clocking in the shift, and so internally there's a shift to the register, and it will shift in whatever. And then I want to then put that onto the outputs as soon as I can, so then I have a short delay, and then there's a latch pulse, so that I latch the internal register to the output register. So that's what I'm hoping for. So it doesn't really matter how big these pulses are. They could be quite small. it's just all that matters is the rising edge. So when these rise from being a low voltage to a high voltage, that's what causes the clock in this particular IC. So the 74HC595. So I can note a few things. That if this is actually the case, and if this is working, there's several sorts of states we can be in. We can either be in this state here, where both the voltage going into the shift clock pin and the latch clock pin are both high. So this is stable, they're both high, they're not changing. And over here, they're both low and they're not changing. But in this area here, the voltage going in, we'll go with this one here, the voltage going in is the shift is high and the latch is low. So that's what this area is. All right. And over here, the latch is high and the shift is low. So there's two different sorts of scenarios here. And all that I really care about is that one of these things happen. Like most important, I want this thing here to happen. But I'm going to say because they're shifted by a little bit, both of these things should happen, but I really care about this. So I want to see the case where the latch has gone high, but the shift has gone high, but the latch has yet to go high, and then it will go high later on. And I don't want to see this being the case all the time. So it only happens in one little small bit here. So I wrote this out originally, and I wrote it out using the sort of logical way of doing it. When I mean by logical way, I mean using sort of logic language. So this is kind of leading into Boolean logic, and Boolean logic is all about ands and ors, and turning sentences in English into sort of mathematical equations. But they're not exactly the same as mathematics, but they work in a kind of the same way. A sort of analytical, methodical way of analyzing things. And this kind of stuff appears, as we're going to see, in everything, in computer science and philosophy and all sorts of things. So in this sort of thing, you have two sort of states. That's what Boolean is really based around, two different states, true or false. But we can map that onto the digital domain by saying that high, for example, is true and low is false. So in this case here, the shift pulse is true and not the latch pulse. I don't know if that's going to make sense, but that's what this is here. So we've got a shift pulse high and not the latch pulse high. So if you can say something is low, it's you can put the not in front of it and say not high. So low means not high. I don't know if that really helps, but it's just that it will help leading on to other projects, and it's the way that I've written it in a couple of these things. But first, next thing we're going to talk about, so that was sort of the general theory. It doesn't really make sense at the moment to think about this, so don't get confused. But just think, I'm interested particularly in this area here, where the shift pulse is high, and the latch pulse is low, or you could say, or the latch pulse is not high. So before we get in any further, we're going to talk about gates. So I'm going to start with this one actually. So the first gate we've talked about, and it's a funny word, but it goes back to a sort of representation of Boolean logic inside digital stuff. And you can kind of imagine it's a gate because information is going in this side and it's going through a gate and it's coming out the other side in a particular form. So it's being transformed by something. So this gate is transforming things. The one we've already met, which is the 4049 a couple of times, is an inverter. So it inverts the voltages from low to high. So if your input going in is low, the output is high, and if the input is high, the output is low. But you can also see this as a NOT gate. So a basic form of gate is the NOT gate. So if you imagine that high means true and low means false, then if you feed in a true signal, which is a high signal, this is not always the case. This is positive logic, but you could have it the other way around, where you think that false is a high voltage and a low voltage is true. But we're going to stick with just looking at it this way. and this seems the most logical way of thinking about things, but sometimes you might want to think the opposite way around if it's easier to build a circuit. So another way of looking at an inverter is as a NOT gate. So in here we send in, if we put in a true, we get false, and if we get false, we get out true. And that kind of like relates to language. If I can say if X is true, then not X is false, and if X is false, then not X is true. So a way of saying that is, if I say that X is it's raining, if it's how's that going to work? So if it's is that a good thing to say? I might say actually this pen is blue. So that's my statement, and that statement is false. But it is, if I say not this pen is blue, then that statement is true. I don't know if that helps, and I don't know if I should really get too much into that kind of stuff. But that's the sort of basic idea behind a NOT gate. But another kind of gate, which is an interesting one, is the AND gate. So in this case here, this is a different kind of gate in that it has two inputs and one output. So they pretty much all have one output, but they can have multiple inputs. It's not, I'm not going to guarantee that that's true, but most of the time you can turn anything that has a multiple output into a combination of things that have only one output, if that makes sense. But today we're talking about AND gates. We're not going to get too bogged down, though I am so far. So in this case here, there's one in and there's two in, and these can be both low or high, or you can imagine them as true or false. And I think talking about that as true or false makes the name make a lot more sense. So if you think about them as being, so in this case here, you kind of have to imagine that true is a high voltage and false is the low voltage. So if you look at it in terms of digital electronics, we've got low, low. So we've got low for one in, and then we've got two in is also low. Then the output will be low. But it makes a bit more sense if we think about it in terms of true and false. So in this case here, in one is false. In two, I'm going to switch it around. I just wrote one in and two in because I thought it might make it easier to read, but I don't think it is. It's easier to say in two and in one. So if in one and in two are both false, then the output is false, and that makes sense. Like if you have to say that something and something is true, so something and something is true only if, so if I say X and Y is true, so whatever X is, so X might be it's raining, and Y might be this pen is blue. X and Y is only true if each of X and Y is true, which it sounds really terrible, but it's just a way of sort of breaking down statements so you can say and analyzing things. So in this case here, if my X was false and my Y was false, then X and Y is also false. But if one of them is true, so in this case here, if X, I'm going to start calling this X. So if X is false but Y is true, then X and Y is still false because X is false. Same thing for the case where X is true and Y is false, then the answer is false. But if both of them are true, then X and Y is true. So you're thinking about turning it into X and Y as a statement, as a little tiny subunit. We're breaking it down. I'm just going to write it here. So we've got, I don't want to write there because I'll get it all over the piece of paper, because this pen goes through everything. X, Y, and X, and Y. So they're two separate little things, really. You've got X, Y, and then this little unit, and you're kind of treating them all as individual tiny things when you're saying either this whole thing is true, this thing is true, this thing is true, this thing is false, and so on. But digitally you get the same kind of thing. You get low, 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 so low and low is low, low and high is low, high and low is low, and high is high. So they kind of match across like this. And I hope that's kind of made a little bit of sense. And then, because that will make the next bit make a bit more sense. Though I feel like I'm missing one piece of paper. I am missing a piece of paper. Hold on a second. I'm sure I had one more. Oh, this is a bit rubbish. Well, we're just going to have to make do. I think there should be two. Going back. Oh no, I think I only had 4 pieces of paper. So going back to here, I want to turn this sentence into something using digital logic. So I want to say the shift pulse and not the latch pulse. So in this case I want the shift pulse being high and the latch pulse being low. And the way we could do that is we can combine the two. So this is how you draw the symbols. I don't think I really emphasized. That's how you draw the inverter or the NOT gate, digitally speaking. And this is how you do it, how you draw the AND gate. So it's this little round circle thing with a flat bottom. So this actually matters. So there are some that has a little curved bits and they're a bit pointier. We're going to get to the other kind of gates later on. But if we combine them together, we get this kind of figure here. So A. So if we want A and not B, so this here is A. So this thing is only going to output a high voltage in a particular case. So thinking digitally, which I think is easier because I run out of time otherwise, if A is high, right, and B is high, well, if B is high, we'll go through here. B is high, then this is going to be low. So we've got a low here, and we've got a high here. And this is an AND gate. So low and high is a low answer. So we get low here. So if B is true, then not B is false. All right. So if something is true, then the not of that is not true. If so B is true, then not true, not B is false, and A is true. You've got false and true, so the answer is false. But there is one case. So another way of looking at this: if this was false and this was false, then if B is false, then not B is true. So if you can imagine that if B was, my pen is blue, then not my pen is blue is true. I think we've been through that. Then you get the answer that is going to be true, and that is going to be false, and that is going to be false on the output. But the last thing is if A is high or true, and B is low or false, all right, then B being low, that will be high there, so you'll get 2 highs here, and the output will be high. I hope, and which is the situation we have here. So I don't know if I should have actually gone through and talked about the Boolean stuff. I think I made it very confusing, but we'll just stick with this. We'll just say here that A is high, right, and B is low, goes into the inverter, comes out high. Alright, so then we've got 2 highs going into here, and then we'll get a high coming out. But in every other situation, so if both of these are low, we can count every case where the A is low as giving a low output. If we go through our complicated gate here, if both these are high, then the input here, if B is high, then the input here will be low, and so we'll get a low output. So this always gives it, every time that B is high, we get a low output, and every time that A is low, we get a low output. And the only time we'll get a high output if we put something through these gates here is when A is high and B is low. And that's what we want. So what we're going to do is we're going to feed the clock pulse of both the shift and the clock pulses into our little complicated gate thing. It's not that complicated, but into our gate. and then we're gonna monitor that. So what we should see once we've done this is little pulses just in this area here. So our output from our gate is going to be mostly flat. I'm going to draw it here. It's going to be mostly flat for this part here, and this part here, and that part there, and it's only going to come up and be high in this particular region here. So it's only going to be high when we're here. And if our little circuit doesn't actually work and these things match up, then there isn't really going to be a clock pulse. At least nothing that's going to show up on my scope, because there might be like a small tiny fraction of one, because electricity takes a while to go through things, I don't know, but the scope's not going to be able to pick that up. So if there is no case where these two things happen, you're going to see it's all going to be flat. And so it's all going to be low voltage, and it's not going to have these little pulses here. So that's how we're going to test it. And so the next thing is, this is taking a lot longer than I thought it was going to take. I thought it was going to be way, way easier. So how are we going to test? I don't think we're actually going to get around to doing it tonight, which is fine. But how can we do this? How can we do an AND gate? So we've already gone through the CMOS 4049 and the very similar 4069, which we haven't used, but they are kind of similar. For getting this inverter thing. So we've already seen this gate in an IC form. What can we use? What on earth have I done with the book? Well, what IC do we use for this thing here? Well, we'll go to our CMOS thing. It's probably easier if I found a page in here that has it. Oh, they've got a nice little picture there. Well, we won't go through that, but there's a whole bunch of gates. So they're talking about that, and they've actually given the number away. I'm going to turn it around so you don't get confused. So there's our hex inverting buffer, which is the 4049, which is similar to the 4069, which is there. So there's a little picture. So they use the exact same picture, but symbol that I've just used. But we want the quad 2 input AND gate. So if you can see very closely, that's the symbol that I've used in here. So this is the AND gate, and this is the 4081. So what we're going to be using, well, I would like to use actually the 4081 because I wanted to stick with the 4000 series, but I don't actually have any 4081s, so we won't be using this IC. But what we will be using, because strangely enough I have an awful lot of these ones, is, I'm going to find it in here, probably should have marked the page out, well, it's going to look like I'm using a TTL chip. So this is written here as a TTL chip. The 7408, but we're not going to use the 7408, we're going to use a 74HC595. So I haven't talked about too much, but the 74 things are all from a different type of logic, or not, a different type of digital circuit called TTL ones. But they do have a series which are the exact same layout, but they're CMOS chips. And so they have HC in the middle of them. And so here is a whole bunch of these things. So these are 74HC08. So which makes sense because we're working with the 74HC595. It'd be kind of interesting to see if they've laid them out. They're a little bit rude about this kind of stuff because they've laid them out completely the opposite way around. They do have, I don't know if it's going to show up in the camera, but they do have VCC, or the positive voltage, on pin 14, and they do have ground on pin 7. So they both got the voltage pins, the power pins, on the correct place, same place. But then they go and do the strange thing where they flip them around. So in this case here, we've got an input on pin 10 and we've got an input on pin 9, which they do have an input on pin 9 on that one, but in this case here the output is pin 8, and on this one here the input is pin 8, and the output is pin 10. So they had them in the same place, but they're flipped upside down. So they work very similar, but they're just the other way around. So that should be okay. So what we do on this chip is not going to be that different to what I would do if I had a 4081. The only thing is the 4000 series, they can accept a much wider range of voltages. So these only go, I think, from something like 2 volts or 3 volts to 6 volts or something like that. TTL logic ones don't, they're much more confined. But the CMOS versions have a bit of a wider range. But the 4000 series ones, I think, go up quite a lot higher, like to 15 volts or something. So that's kind of cool. But in my case, I'm just using the whole way through 5 volts, so it doesn't really matter. So we're going to use this one, but we've run out of time to actually do it. So we're going to come back for the next video, and we're actually going to build a little circuit, and we're going to see if we can get those clock pulses on our oscilloscope. So that was way too long-winded, but I hope it was kind of helpful. Everything will become much easier if you Google stuff or look it up in a book or something like that. And if you just watch this channel, we'll eventually get everything sussed out. But we're going to talk about, like, because I want to do a lot more coding on Arduinos and AND gates. Oh, I had a little picture. Where did I put it? Oh yeah, down here. So these are just two different ways of writing what I just said with the A and B and AND gates and stuff. So this is how you might do it in logic. I think that's how you do a NOT. I've forgotten. It's been a while. So it's a tilde symbol. I had to add it in because I forgot it. So that's the intersection. So in this case, this is kind of set theory. So this is A. So you can imagine also in mathematics and set theory, if you have set A and set B, what's in set A and set B? Well, that's the intersection. That's the intersection symbol there. And this is the computer sciencey way that you might do in your Arduino. You might write A and not B. And so these things come up quite a lot if you do low-level coding, which we will be doing some of. So you're bound to see some actual usage of this in two different ways in coding. We'll come back to that in future videos. So it will all make sense one day. But I'm going to leave it there, and we'll come back next time and do some fun with our 74HC595 and our 4049, which is sitting over there, and our 74HC595, and then we're going to get this thing worked out. And then later on, we are going to continue with this video with this thing here. So I'm just going to give it a little bit, because I've got 1 minute left, a little bit of a prelude to what's going to happen. So the only problem with this thing here is when you turn it on and you press a button, it only actually makes a difference when it's clocking it in. Which is kind of unintuitive. So I want to turn one on, but it only turns it on when it's clocked in. So it's on that clock pulse that it's actually reading the button. And I'd like it so that when I press the button, the first one becomes on at that particular time as soon as I press the button. Or if I press this one, the first one becomes off straight away, and then it starts shifting it along, which makes a lot more intuitive sense. But it would be a little bit harder to do this with digital circuits. So we're going to look into how we can do that, and I think we can come up with a pretty easy way of doing it. But that's going to be a later video, and it's just for fun, just for learning about new ICs and stuff like that. When you have this going quite fast, it really doesn't matter at all. But anyway, thanks for watching, and like, share, and subscribe. We're almost squashed the IC. Bye!